we're back in the usual setup. So C where QP is algebraically closed and complete and etc. We'll still C flat. What else do we have? We have residue field K. We have L, ring of bit vectors, and we're at P. And most importantly, we have A-inf, which is a ring of bit vectors, plus a ring of integers of C flat. And recall that we wanted to prove this theorem of Farg that Roy Keesing modules over A-inf are equivalent to pairs T psi, where T is a finite free ZP module and psi and T tensor Theorem is a Theorem plus lattice. And so in the last lectures we already have identified this category was the category of E over Y, where Y was the p-adic spectrum of A-inf, removes the closed point. A vector bundle plus phi E from the phi pullback of E to E and isomorphism on Y remove this point xc. Okay. And so what remains to do is just to extend this vector bundle to a finite free A-inf module. So so in the beginning of this semester, I was suggesting the strategy of proving this theorem of Farg, and I asked Kedlaya whether he could prove this result, and so he came up with a proof immediately, essentially. So, for the theorem of Kedlaya, that finite free A-inf modules go equivalently by passing to this open subset Y to vector bundles. And so you should regard this as an analog of the following classical result in commutative algebra. So if R with the maximal ideal M is a two-dimensional regular local ring, then finite free R modules go isomorphically to vector bundles on the punctured spectrum. So all of them extend to vector bundles over the puncture. Like there is an abstract way to prove this by saying that any such guy extends to some reflexive module here. A reflexive module has depths at least 2. Then you just use Auslander-Buchsbaum, which says that depth plus projective dimension is the dimension of this ring, and so it sees that the projective dimension has to be 0, and hence it's projective and free because it's a local ring. But like that's way overkill, really. And so the proof I will give for the theorem of Kedlaya actually somehow it also works in this classical setup. So yeah, so let's first somehow prove the algebraic version of this result. So, finite 3A inf modules go isomorphically to vector bundles. Or not the adic spectrum, but the usual spectrum as a scheme of the remove the maximal ideal. Okay. All right. So let R be this ring A in, and we will use.
What is the difference between the two statements?
The inf is not.
Well, I mean here
No,
you some.
this is a scheme, and that's an adic space.
Yeah. So I mean this is covered by some complete rings, and there is covered by just invert algebraic elements. And so we can cover this punctured spectrum by two affine subsets, where R is, say, the one where you invert P in R, R2 is the one where you invert this element by flat, and R12 is the one where you do both. And so, so I should say that because R is the intersection of R1 and R2 in R12, as everything is somewhere here. That's easy to check. You see that this functor is fully phaseful. Because you can recover this module as a global sections of this vector bundle. So to prove essential surjectivity, let's start with some vector bundle. So if you have a vector bundle on this punctured spectrum, then you can evaluate it on all these affine subsets, and so it's equivalent to the datum of M1, so Mi, a finite projective Ri module, or I12 or 12. Such that M12 is really just the base extension. And then the only chance for this finite 3A inf module would be to take M, the kernel of the map from M1 plus M2, M12, sending xy to x minus 1. Right? Okay. And so note that some of from abstract algebraic geometry you already know that if you base extend again to Mi, then this is to Ri, then this gives basis module Mi. So it's just the adjunction if you have the inclusion. Let's back R into M. Just back R. That pulling back the J lower star as the identity. Okay. Good. So the first thing we'd like to see is that M is not all too big. And so for this I would like to say that M is in some sense bounded inside of the M1 and M2. And so for this I need to recall a little bit of topology. So if A is any Tate ring with F and A topologically nilpotent unit, and A0 and A ring of definition. So recall that this in particular means that A0 has the f-adic topology and A is A0 invert F. Then if M is any finite projective A module, it carries a canonical topology. One way to define this is to note that you can write M as a direct summand of some free module A to the n, and then A to the n has a canonical topology, and you can look at the subspace topology as a direct summand or the quotient topology, and they agree. It's induced. And so let me note some facts in the situation. So if A is complete, then also any M is complete. And A0 submodule N inside of M is open if and only if you invert F, you get M. Because then any set of generators of this module, some F power will already live in there, and then you get this. And an A0 submodule N is bounded if and only if it is contained in a finitely generated A0 submodule. And then all open and bounded submodules M0 of M, they all differ by bounded F torsion, meaning that if you have two, then an F power of 1 will be contained in the other. And they are f-adically complete. If A is.
Any homomorphism is automatic.
Any homomorphism between finite projective modules is automatically continuous also. And any surjection is open.
There's
differ by numbers F portion.
Right. If you have M0 and M0 prime, such guys, then there exists some n such that f to the n M0 is contained in M0 prime is contained in to the minus n M0.
And the n does not depend on either.
Well, no, of course they depend on the lattices, right? But they don't depend on some of the elements you choose. Right? So if say one would be containing the other already, then it would mean that the quotient is then killed by a bounded power of f. And I guess all of this is pretty straightforward to check. Okay, and so an intermediate claim is that M, which is contained in Mi, is open bounded. Where we endow R1 with a p-adic topology, making R ring of definition and R2 with the p-flat adic. Which then gives such a topology on the MIs, and hence it makes sense to ask that M is open and bounded. So it's open is okay as M tensor R Ri is Mi. So M generates Mi. And why is it bounded? So for this, the idea is that M2 is somehow bounded in the p-adic direction. So that's okay. So I mean, it really doesn't really matter which I choose. Let's do it for I equal to 1. Bounded. So let's endow R12 with the p-adic topology. No, sorry, with the. So I want to show that this is. Sorry. Making R2 open bounded. No, making R. Now I'm totally confused. R2?
Can you repeat how we know that M tensor I is Mi?
Well, I think that's true for any quasi-compact open immersion of schemes.
I mean, you can just quickly say that.
I mean, if you have, you want to construct lots of elements in here, and if you have any element of M1, that gives you an element of M12, and some p-flat power of it will come from M2, because M12 is just M2 invert, invert p. And so some p power of any element in M1 will be an M. And so that proves that if you R2, I have an inverted p there, so it makes sense to endowed with this topology. Okay. So then, with this topology, M1 contained in M12 is open and bounded. Because this is And M2 is finally generated over R2, so it's bounded and it's open because it generates the whole thing. And so this should imply that then if I intersect M2 with M1, which is then a subspace of M1, and by the way this is M, is also bounded. And here you use it. Again, this is some, whenever you want to check something for such finite projective modules, it's enough to check it in the free case by writing something as direct sum of something free. So. X and R12 is bounded.
So the topology on M2 is literally its own p-adic topology.
The topology, what?
On M2, its topology from M1-2 is literally its own intrinsic p-adic topology.
It's p-adic topology. But it's
somewhat
originally we endowed M2 as we can also endow M2 as a topology as an R2 module, and that's different because that's a pi-flat adic.
Right,
So it's a bit tricky.
but right now M2 is just being...
M2 has p-adic topology, but it's not complete for that.
Yeah.
Then X intersected with M prime is bounded. This you can reduce to M prime being free, thus to M prime being R1. And then X is contained in some p to the minus n times R1, 2. And then X intersected with R1 is p to the minus n. R2. And then if you intersect R1 with R2, we said we get R, so if you intersect X with R1 here, I get p to the minus n R. And R1 is bounded.
R1 is just contained in Peter Scholze.
Yeah.
Thank you. Okay, the picture is really just that R is somewhere here. Then if I invert P, I get R1, that's somewhere, all of this is somewhere considered as stuff in R1. Like if I consider elements. And then I have R2 would go somewhere here. And, well, I think this picture is not helpful. Okay, so finally we see that this guy is open and bounded in all of these guys. And so thus M is p-adically complete. And if you want, it's also pi-flat adic. And thus also complete for the composite. Also, M, which is contained in M1, is p-torsion free. And so this means that to prove M free, it is enough to prove that M of P is free over R mod P. We call that this is the ring of bit vectors of OC flat mod P, so it's just OC flat.
Where is the p-adic completeness coming from?
It's bounded inside, open and bounded inside M1, and I said that open and bounded submodules are f-adically complete if the ring is. Okay, and so the next claim is that M mod P injects into M2 mod P, which is like M2 lives over R2, and then mod P, this is C flat. And so this guy here is a d-dimensional C flat vector space. So assume we have an element M and M such that M maps to 0 as an element in M2 mod P. Then M can be written as P times an element, let's call it M2 prime, where M2 prime is an element of M2. And then M prime, which I define to be M over P and M2 prime. So in R1 I can invert P, so that's well defined there. So that lies in the kernel of M1 plus M2 to M12. So in M2 I can divide by P by assumption, and then on the other side I can always do it. And so that was M. And so this implies that M is equal to P times M prime. And so, which gives the claim. Okay. And so, this guy here is some OC flat submodule, which is open and bounded, and we want to show sphere of rank D, and if C flat of discrete values, it's more obvious.
So for the classical theorem, this is rules itself.
Yeah, for the classical theorem, that here we can stop here. Any open and bounded, let's say lambda inside of some C flat to the D is isomorphic to ring of integers to the D. So, would be done. Which handles the classical case, at least for complete regular local rings. And so we need to go on because in our case, this lambda could be like, if this was just C flat, it could be like the maximal idea in the ring of integers. And so that's not free. Or it could be a set of elements of some variation strictly via some arbitrary real number, and this real number could be someone not in the value group, etc. But there's the following useful characterization of free guys. So this works for any non-Archimedean field in place of C flat. So let lambda C flat to some D be any actually or C flat submodule. Then the dimension over the residue field, lambda tensor to the residue field, is always at most D with equality if and only if lambda is free of rank D. Let's also prove this. So let's first induct, so reduce to d equal 1 by induction. So if d is greater than 1, let's choose some w inside of, let's call this guy v, c flat to the d, which is non-zero and not the whole thing. And then this lambda induces lattices, or open and bounded sub, well no, it's not even necessary that it's open and bounded, it just induces some sub guys. Lambda w, which is lambda intersected with w inside of w, and lambda v mod w be the image of lambda inside of w.
V mod W.
V mod w, thank you. And so we have an exact sequence, 0 goes to lambda w, goes to lambda v mod w, goes to 0. And everything is flat over OC flat. Because it's contained in vector spaces over the fraction field. And so I can tensor this with the residue field. And it's still exact. And so this implies this dimension inequality. Dimension lambda tilde k. And equality can only happen if lambda is an extension of OC flats, because those two guys would be, but any such guy is itself OC flat. And of course, that is satisfied, so dimension inequality is an equality. It's a variation ring of rank 1. Do I need rank 1 for this? Well, any variation ring would be fine, I think.
And then any projective finally generated is automatically free.
Well, it's a local ring. It's certainly local. For this last implication, local is or do I need even local? Well, I don't think you need anything. Okay, and so if d is 1, then either this lambda is a whole guy, in which case lambda tensor k is 0, or without loss of generality, like by rescaling, I can assume that lambda is contained in OC flat. Is an ideal. And so ideals in such a guy come in two sorts. So either lambda is a set of elements x in OC flat, but that's the absolute value of x, that knows the absolute value of y, for some y in OC flat. So it's a principal ideal. So that's y OC flat. So then lambda is isomorphic to OC flat, and dimension lambda tensor k is 1. Or lambda is a set of elements such that the absolute value is strictly less than some real number r. But then any x which absolute value less than r can be written as epsilon times y, where the absolute value of y is still less than r, and epsilon is an element of the maximal ideal of C flat. Where because this is not discretely valued, we can choose the absolute value of epsilon to be, well, it's less than 1, but strictly larger than x over r. And so this implies that lambda tensor k is 0. Okay. So it remains to prove that the dimension over the residue field of M mod P tensor over OC flat to K was equal to D, or it's even good enough that it's greater or equal to D. On the other hand, this is also just the dimension over K of M tensor over the whole guide down to K. So we'll consider this. Okay, and so now we're doing a similar argument, not mod P, but mod P flat. So M tensor R W of K subjects onto some lattice T contained in, let's write V for this, the reduction of M1 to WK inverse P. Where this gadget here is open and bounded. And so this is finite field rank D. So it's mostly just some, well, it's called L. We call it L was. Okay, it's okay inverse P. And now L is discretely valued. And so we have an open bounded subguide here. So so T really is isomorphic to W of K to the D. And so this implies that M tensor K surjects onto T tensor K because tensoring is right exact. But this is just K to the D, and so it gets a complete. Good.
Maybe you should say this is a little bit simpler than the proofs that I sent you because I didn't have the lemma. I
Yes.
had to do something more complicated.
And also you try to reduce to the spherically complete case and did some other approximation argumentation. So it's a bit
Yeah,
different.
this basically takes care of that.
Yeah. Well, I mean, somehow in your argument, I didn't see how you prove that this cannot happen, but I don't know. I mean,
No,
it works.
It's no longer an issue.
So the funny thing about the situation is that, I mean, a priori you would maybe like to argue that this
Open? Wait, this image is open from...
of course, like the p-adic topology here, because this is like openly bounded. But this contains like the image of like the M is contained in M1, and some height of p power of any standard lattice is contained in M because it's open.
Oh, okay.
M was open there. I mean, M when you got p get everything. Like if you write p, you get an isomorphism.
Where does P come from?
It's the image.
Oh, geez, defined into the image.
Yes.
Yeah, so as soon as you know that it's open and bounded, whatever it is.
Yeah. So a priori it looks like it's easier to argue on this side, but on this side you don't even, I said, don't think it's a priori clear that this map here is injective, as was on the other side. Where on the other side we use some of the p was there. I think it's hard to make a similar argument when like both directions are infinitely ramified.
By the way, the statement's not true in that case.
It's not true, you know
I don't
that?
actually know, but it would guess
Probably
that
it's not true, yeah.
But when you do it the other way around, I mean, what is the ring, the field that comes up?
L or?
Yeah, what is L replaced by? I mean, here you,
C flat.
On the one side it was C flat, on this side it's L.
right, and now if you do it the other way around, then,
What the,
Whatever.
well, what, I mean,
We don't have to.
they're just L and C flat, and you might try to mutate them.
uh,
Well, it's fine that they give you complementary information, which in the end exactly is enough. I don't know.
I mean, here you prove that M is open and bounded in M1, right?
M is also open and bounded in M2 if you want. I proved that also.
Oh, maybe.
I didn't actually need it, I think, because this lemma there worked for any OC flat submodule there. So I think what I needed was just that M is open and bounded in M1. Because that also implies
Okay, that's something I don't understand.
Okay. Good. So now we know the algebraic version, and now we want to prove this analytic version. So recall that we want to prove that find free ANT modules.
So this book will not work for the AN tensor OCP, for example.
Right, that's what I meant. If you tensor this again into a direction where both directions are now infinitely ramified, then it's not even clear whether it should be true. But
Yeah, I would guess that it's false.
fortunately, a typo module is usually a ZP module and not a C flat module. Or CP module. What do we want to do? So we want to prove the 5 free AN modules go isomorphically to vector bundles on Y. Yeah, that's the statement. Let me just say what you need to prove for fully faithfulness, and so not so hard. So how can we understand vector bundles on Y in roughly the similar way as we did understand vector bundles on this punctured spectrum? So Y can be written as the union of Y0, 1 and Y1 infinity with intersection Y1, 1. Just do some reasonable space. So call the picture. So here's the close point. We're taking that out. Then there was this map kappa, which I now normalized to have 0 here and infinity here. And then there was, here's this locus where p is equal to 0, p flat is equal to 0. And here's a locus where p is equal to 0. And then somewhere here is 1. And we have two affine subsets if we're taking the pre-images of these intervals there. And so what are these guys really? So to have similar notation to the first proof, it's better to call this S2. This is the adic spectrum of some S1. And this will be the adic spectrum of some S1, 2. And what are the rings? So the rings are so I should say that what are really these subsets? So that's the locus where I suppose now p flat is less or equal to p is 1, 0. Y1 infinity is the locus where the complement happens. And I should have written it, well, no, let's keep it this way, but like this corresponds to this guy, and this corresponds to the guy we'll write next, so I apologize for that. And y11 is the locus where they're equal. Their absolute values, non-zero. So it's this guy, and then you also invert p again. Here you do the opposite. And S12 is where you join like both of these guys. And then you invert one or equivalently both, or either or both of these guys. Let's do it in a symmetric way. So the statement you need is that A-inf is really the intersection of S1 and S2, which both of map injectively into S12. And now, today I even have a reference for this result. Kedlaya Liu. Lemma 5211C. And so, as before in the algebraic case, it proves fully faithfulness. Because it means that we recover the module as a global section of spectrum bundle.
I suppose it's worth reminding, the reason why you have to actually make some argument for this intersection is because you don't have canonical series representations.
Yes, so for which ring is this most important here?
Well,
S1 is a problem.
yeah, S1. Gets
Yeah, so you would think that this, usually when you have such a Tate algebra, you can represent elements as some kind of formal power series, but that's wrong in this case. It is true, I think, for S2.
Yeah.
Why is it wrong for S1?
Yeah, because P is so strange. I mean, the bit vector addition somehow screws me up. Okay, and so now we want to prove essential selectivity. And so a vector bundle E on Y by this gluing result of Kedlaya and U for vector bundles. On each of these affinoid subsets, it's really given by a finite projective module. So E1, a finite projective S, so EI, finite projective SI module. For I being 1, 2, or 1, 2, plus an isomorphism between EI and the base extension to S1, 2. for I being 1 or 2. And now we actually do a very funny argument. So we want to reduce to the algebraic doing, and so first of all we want to produce finite projective modules over R where we just algebraically invert P. So let's consider again let's first do it for R1 and a similar argument for R2. So consider again R1, which was, I recall, A invert P. But now we endow this again with its p-adic topology. P-adic topology. So we're really cheating here with the topologies. And so you also have this adic spectrum of R1, but it does not map to the adic spectrum of A-inf because the topologies are incompatible. But still, it is covered by the open subsets as there pi flat.
This is really SPA R1 comma A-inf prime.
Yeah. Because those are, like, in general, these are supposed to be the power bounded elements when I not write something, and check that these are non-zero. And of course, the intersection is the locus where the absolute values are equal. And so, now this part again corresponds to the adic spectrum of. No, I get my notes the wrong way around. I'm confused. How does the
Which point is
did these arrows go right?
those arrows are switched. That arrow is
Like they really correspond like they're written?
Yeah.
Yeah, wonderful.
yeah, okay.
Sorry.
But over there you said S2 corresponds to 0, 1.
That needs to be switched.
Z needs to be switched, but that's nice because it's anyway the better way to have this way around. Great.
That
Does this all work now? I think that's good, yeah. Wonderful. Sorry. So that part is still the adic spectrum of S1. Why? Because on this part, P flat is less or equal to P, so if P is topologically equal and P flat is the same, and so like there's no difference now between the p-adic topology and the p flat adic topology. But this gated theorem might a priori have nothing to do with what we're getting on the other side, because here we're just regarding P as topological input and not P flat. But surprisingly, this is really just SPA S2 invert P. Why? Why? You just compute it, and so let's do this. So
maybe you want to say what the plus ring is?
the plus ring has to be the correct thing, I think.
I mean, that might help clarify what's going on.
Let's call this SPA S2 prime for the moment.
Okay.
And so what is the abstract definition of S2 prime? So S2 prime, the recipe is the following. We take A-inf, we take this open bounded subring here, we adjoin the same element there. I'm sorry, Jared, for this. And we complete for the p-adic topology. And then after we've done all that, we again invert the we invert P and also P flat, I suppose. Sorry, no, we What?
That's the thing that's not.
If I invert P, I also have inverted P flat anyway, right? So I invert P. Yeah.
Why are you?
Because this R1 is like A
R1,
invert P.
sorry.
And, yeah. You agree with that formula? And so the miracle that happens is that this is actually the same as taking A inf, P over P flat, and completing for the PP flat adic topology, which would be the same thing as the P flat adic topology, because now here P is divisible by P flat.
Maybe the ZP bracket T version of this would be easier to see.
Well, so let's check this.
I'm not clear why you have P instead of section where P.
Because R1 has the
R1 is already P inverted.
But this is
And if I invert P, then I also invert P flat, because like 1 over P times this.
Oh yeah. Oh yeah, they are the same. Yeah.
Okay?
Oh, and this is within spot R1 anyway.
Can I explain?
Right. Oh, P is not zero.
Yeah, maybe
Yeah,
like,
I see.
writing this is somehow not
No,
useful, but anyway. So to check this equality here, we have to check that if we take A inf, algebraically adjoint this P over P flat, and then mod out by P to the H P to the N, that this is already by flat adically complete. And because this guy is like flat over Z mod P to the N, and yeah, it's enough to do this for N equal to 1. And there we get, well, we can do this mod P first, and then we adjoin one variable T, which is subject to the relation that P flat times it is P. This will go on. And so P is already 0, so this equation is just, well, A inf mod P is just OC flat, and then I adjoin a variable T, subject to the relation that T times P flat is 0. Or like if I write this in terms of monomials, it's OC flat for the constant term, and then in positive degrees I get just OC flat mod P flat. Yeah, and this module is p-adic complete because like this is P flat torsion, so it's okay, and this guy is already p-adic complete.
And I guess you check the P flat adic separatedness just by inspection of the.
Yeah, complete and separated. So I guess what I check at each step is that the lim is what it's supposed to be, and there's no R1 lim if you want. And so I think this proves as an inequality, and so this means that this S2 prime is really just S2 invert P. And also the guy with the intersection is just this S12 again, there's no problem with that. And so, if you take E1, E2 invert P, and E12, they define a gluing datum for a vector bundle on the adic spectrum of R1. And so because this guy here is sheafy, that's what I checked in the last lecture actually. They glue to a finite projective R1 module. And now we're essentially done. We just have to do the same thing all again. So similarly, if you take E1 and red pi flat, E2 and E12 glue to finite projective. Let's call this M1 here. Finite projective R2 module. M2, and well, similarly, you can also get an M1 too. And so we get a vector bundle now on the punctured algebraic spectrum. And so we conclude by the lemma. In the algebraic case. Great. I guess this was taking me less time than I expected.
So how much does it differ from Park's proof?
Yes, that's a good question.
What?
How much is different from your proof?
This is very different.
Okay.
I mean, at this point,
Yeah.
But I use some Kedaya matrix factorization. That
So do you also prove this extension of vector bundles result?
No.
No.
I'm gonna.
But you prove it for Stukas or something like this. I mean, you have to, right? I mean, I had in mind that you have some reduction to the rank 1 case at some point, or?
I know I have to prove that some vector bundle on the Y.
Yes.
Is free.
Uh-huh.
For
Ah.
this, I have to reduce to the rank 1 case, which is very instructive in fact. And because this is how I found the conjecture on the theorem. And for the rank 1 case, it is done with 10
Uh-huh. Yeah, I guess a different way of saying what this means, that all these vector bundles on Y are trivial, is to giving them, I suppose E1 and E2 have to be trivial anyway, although I'm not sure. And then the gluing datum is just some matrix over like S12, and then you have to factorize this matrix over S12 into one which comes from S1 and one which comes from S2.
Exactly, this is more or less what I use. It's more or less instead. I think it's the I'm not sure.
No, but I think it's a very nice application of this results that you can glue vector bundles on these things.
Yeah, so probably this kind of matrix factorization argument translated over to here.
I mean, these gluing results, of course, involve all of these, like, have built into them, like, all these matrix
What I
factorizations.
use is that GNN of, I'm trying to remember, GNN of Roba is GNN of Roba bounded times GNN of B plus.
Uh-huh.
Right. Something like that.
That's, yeah. Mhm.
I have to do
Well, I guess now that we're at it, so I can ask the following question, which I think would be interesting. Like, why?
Result that any vector bundle on this Y is trivial?
Yeah, any vector bundle on this Y is trivial. That's somewhat equivalent to the theorem. This is equivalent to the theorem.
Which Y? So your Y.
This Y which occurred here. There's no consensus about notation. I'm sorry. All right. So So I mean, something in this spirit was used by Kesey, and also when he constructed integral models for Shimura varieties. And with Papas, he has this paper, which is probably not available yet, I don't know, where he does something similar for parahoric levels. And I think if you, like in this context, I think the following question would be interesting. So, G over QP is some reductive group. This parahoric model, some G over ZP. Is it true that G torsors in the algebraic sense over AN are the same thing as, well, first of all, G torsors in the punctured spectrum? Or also then as G torsors on Y, if these are defined correctly. And I think over like ZP power series T, Keeson and Papas prove something like this, if I'm not mistaken. Oh. Bargav, can I say something about our stuff?
Sure.
Okay. So now I have 15 minutes, but I don't know what to say, so let's say something.
Wait. I
Actually,
want to ask a question first. I'm not
okay.
into what you're going to say. Is it true in this case that if you have a quasi-compact open subset of spec A in, then any bundle is trivial?
I don't know. Yeah, I know.
So I was going to ask a question that's So when you have one of these G torsors on Y, does that not? Can I not sort of stick G inside? Can I not think of there being an underlying vector bundle?
Sure, I mean you can embed G into GLN and then fix some other chances that it has to fix or something like this. But
okay, so somehow gluing that sort of underlying vector bundle isn't enough to.
I don't think that in itself is enough. Okay. So you have to check that all these. Yeah. I didn't really think about it.
Okay.
I think there's really something to do. Like I think that over ZP power series T, it's, for example, I think absolutely not a formal consequence of extending active lines. Like if it's a reductive group, really, I think then it should be okay, because then, but it's some Tanakian nonsense. Actually, it should be fine. But like if it's really parahoric, then I think there's something to do.
Or you mean if curly G were?
Curly G. Yeah.
Curly. Okay.
Yeah. More questions? So let me say something about work in progress. With Berger, Budd, and Matthew Morrow. About integral p-adic Hodge theory. So the situation here is the following. So it essentially follows from my p-adic Hodge theory paper that the following is true. That if you have X over C, any proper smooth rigid analytic variety is in fact enough. That's not, okay. Let me first write in this place, not say something. Yeah. So then there is a natural Theorem plus lattice. Let's call this psi inside the étale cohomology of X with CP coefficients tensored up to beta Ron. And so by my Peter Scholze paper, this is some finely generated CP module, and so it's a nice situation. And so if C is already defined over, if X is already defined over K, which is discretely valued with perfect residue field, then this psi is really just what you get from the round cohomology. So it's the round cohomology of this model X over K, and then K maps into beta round plus. And so this is just the round comparison isomorphism. But this lattice continues to exist like in the general case, and for this one has to use an algebraization result due to like the result that you can put such guys into families, which is due to Gabber and Conrad. In the situation where we oversee. Otherwise, this is really in my Peter Scholze paper.
Can you say what you mean by natural?
Commutes with space change and exists in families. Using this extra result that somehow everything spreads into families, I think that characterizes it. So you can construct this gadget here as derived the round cohomology of this gadget. Okay, so this means that if you are in this situation, and let's assume for the moment that the étale cohomology is torsion-free, then actually you get such a phi-free ZP module with such a lattice. And hence you get such a, by this theorem, you get such a Brocchiesi module. So, let's say if the étale cohomology is torsion-free. Get some T
Even though it's just mod out by the torsion anyway.
or you could just mod up as a torsion. Maybe it's not as natural, but yeah. I mean, yeah. Let's someone put ourselves in a torsion-free situation.
And somehow this happened without any good reduction.
This so far happens without any good reduction, actually, yes. And so from this you get a Brocchiesi module. HI, let's call this HI over A in X.
You get an isocrystal.
Yeah, and so our theorem is the following. It's not written, but we are convinced that we have all the arguments. So let's put ourselves in a good reduction case. So let X over OC be a proper smooth formal scheme. I mean, the case of algebraic varieties is interesting enough. Somewhat, it doesn't matter for us whether they're algebraic or not. Then part 1 says the following. If all crystalline cohomology groups of X over the special fiber to WK are p-torsion free, then so are all HI. And secondly, in this case, so on the generic fiber we get these Brocchiesi modules over in, and now we can reduce them to to the ring of bit vectors of the residue field. And they become canonically isomorphic to this crystalline cohomology. Completely integral in any cohomological degree over very ramified rings.
So when X does have a smooth model, your crystalline cohomology is this isocrystal and you get, but otherwise, what is this isocrystal? It's this
Well, so in general what happens is that there should be, like, I don't want to claim anything, but there should be a version where everything is just log smooth and like a same as the reduction, maybe even with some horizontal boundary components. And then there should be like log crystalline stuff everywhere, and there should be a comparison between this kind of reduction and the log crystalline cohomology of the special fragment.
Oh, and then the fact that this thing exists always, it just is natural because, well, everything is eventually
Yes.
log
Yes.
crystalline anyway.
Yeah.
This is kind of evidence for the existence of such models. So then you're predicting what their crystalline cohomology is going to
We're predicting what the log crystalline cohomology
You
will
know the
be.
existence of the cohomology,
Well, after iterations.
right? Yeah, well, yeah.
Is this
Yeah.
compatible with correspondences? You have some family of correspondences and you cut out a piece of the same thing happening.
Well, I guess you can use the same thing like for any correspondence, and then like I think it's automatic.
That's the question.
And so I guess it's even new like for case-free surfaces and small characteristic. Yeah.
So Kissen had a graduate student who constructed made some geometric construction of sigma module.
Yeah, so underlying this is a direct construction of this cohomology theory here.
Right. I'm saying, is it similar to that?
I don't know this other construction actually.
What did he do?
Can you formulate this in terms of like Fontaine?
That's a homology theory that I don't remember.
Yeah, so if you invert p, this is just Fontaine's comparison isomorphism.
Yeah, but can
Well-
you always, so to speak, like starting from something, you tensor it up and do some operation and get the other one?
No, this doesn't work.
That doesn't work.
Um,
So in other words, if I did in Fontaine, I just left out this inverting thing, it wouldn't get the same.
do you mean if you somehow you tensor the crystalline representation with a crys and then take a variance, that gives a different lattice? So it definitely gives a different lattice. So to get the correct into a structure, you really have to do this Borgesian stuff. I think I want to say something else also.
Is it an interesting invariant, the difference between these two lattices?
I don't know. Well, for like a p-divisible group over a p-adic field, it like counts the height of like the dimension of the étale of the multiplicative part probably. But,
We didn't fight these, also have some integral statement.
yes, I mean in Faltings, say for p-divisible groups, like he has some integral statement, but there's some ambiguity about the lattice. Like for two p-divisible groups over two adic fields, you can't completely prescribe the lattice. There's some two-torsion you can't describe.
But I mean, his thing was in terms of this Fontaine setup, right?
Yes, right. That's why it's not completely integral. So from this, you can get like a version over a crys which is correct up to some bounded torsion. But I think there was something else I wanted to say, but I didn't. It also means that, like for any two good form models of something with the same generic fiber, the crystalline cohomology is actually identified if it's torsion free. What else do I want to say?
Do you need? Okay, so you need all of them to be torsion. Like if you want to get
And
a
then
statement of some.
Okay, so that's like what I think should be true is that if like H1 and Hi plus 1 are torsion free, then H1 is torsion free here. But because in general this should receive contributions from torsion here and some Tor1 term from the next one in some vague sense. Yeah, let's stop it.